Okay, let's start with tracking.
Give me a grid.
Got it?
There. Target.
Check.
Target.
Check.
Now follow.
You hold up this pen, you say, acquire this, here it is again, right? So you've got two training instances, which is good against different backgrounds. And now from that you've been able to acquire enough of a model that you can actually track the thing. So say that was the problem. I'm given two training images.
Right, but you'd have a hell of a tough time training a robotic policeman if you had to show him every object he was going to do.
Right, well that part's a little bit odd.
Right. But maybe if you were calibrating his lenses, that might be something you would do. So if you had something you knew about and you moved it around in space, then you'd learn something about presumably his optics and stuff like that.
When you have multiple cameras and you want to use them to look at the same object, and then by the fact that it looks different in the different cameras and it shows up at different locations, that can give you an idea about the structure of the object, how far it is, for example. Because one problem, for example, in images is that you only see them flat. You have no idea how far the depth is. And by looking at multiple cameras at the same time, you can get that information. But in order to gather information, you also need to know something about how the cameras are located with respect to each other. And also certain things about, for example, how much zoomed in they are to a particular object and stuff like that. So calibration is a process of figuring out those parameters automatically.
So someone is showing a pen to the robot and trying to track the pen as it moves around. They show the pen, they say target, and then the system is tracking the pen. And tracking is definitely feasible. The recognition part, it depends on what they mean by that target. If the system is to recognize the one object that the robot needs to track, and within that particular field of view, and then track that one object, I think that's pretty reasonable. It's feasible, and it amounts to somehow storing some type of template of the object or some descriptor of it that makes it recognizable.
Being able to track an object that the system has seen from multiple different perspectives and distances, that's theoretically what she would have been doing, showing the pen close, showing it far, showing her in a different hand position, for instance. It actually is possible that a system in that circumstance could track the pen, so the lighting's not changing between the different examples where she's moving the pen. She's trained it under the exact same conditions that she's trying to track it in. So it is actually pretty plausible that some automated system would be able to track an object that it's seen recently and being able to track it over a short period of time after that.
The tracking part is easily what is being done today in this kind of vision work. The basic requirements are that the pen need not move too fast from frame to frame so that we can still find it, and there are lots of systems that have performance that's comparable to this, so this sounds a quite reasonable application. The idea is to you have these templates, you extract them from one frame of the sequence, so you come up with a descriptor of the object, and then you look at the second frame, the frame after that, and the question is, if you go over that image, can you find objects that match that descriptor as close as possible? And clearly there are a couple of issues. If you know that the pen hasn't moved very fast, then you only search in a small part of the image. If you don't know anything about the motion, maybe the pen was moved really quickly from one place to the other in the next frame, then you need to search the whole image. And the problem there is not so much that it takes longer to search a whole image than it takes to search a small neighborhood of the original position, but rather than that there are so many other things in the image that you may run into what are called false positives. So you think you see a pen while there's just a flagpole or who knows what else in the other image, and now you start tracking that instead. Or you have now 10 possible matches that sort of look like pens, but they are completely different objects, and now you need to decide which one is the one you were tracking. So the faster the motion, the more that kind of problems you're going to have. But if you can assume that somehow the motion is smooth or small from frame to frame, then that's definitely feasible. So it's not at all unheard of.
They're in El Camino. There it is. John, give us lat 30, 64 minutes, long 72, 29 minutes.
That's affirmative.
There they are. Coming in from top left. Let's go in there and get them.
That's tracking from satellite imagery. You can tell it's satellite imagery due to the resolution and combined with the very wide field of view. That's very typical of satellite imagery. This is somewhat possible. My gut instinct, though, is that the tracking just looks too smooth. As you can see here, it tracks it pretty much perfectly. An autonomous algorithm generally would be a little bit more jumpier than that, and it actually looked like they synthetically inserted the cars in that small segment right there. Let's see.
Coming in from top left.
That doesn't look real. That looks like they added in that car after the fact. And so they're tracking it perfectly because it wasn't really there in the image to begin with. One of the biggest problems, especially with outdoor video, is cloud coverage. Clouds are the hardest thing to overcome in terms of satellite imagery. Cloud coverage blocking what you want to see on the ground, and clouds casting shadows is also very problematic. A lot of the times as a cloud moves throughout a scene, even if it's a very thin cloud, it actually changes the intensity values enough in the image itself that it becomes hard to develop a background image. And because it's difficult to develop a background image, it is then difficult to do this image, very simple image moving target indication. That doesn't mean that it's not possible, but it just makes it more difficult. And here, of course, they're showing a significantly easier problem where there's absolutely no cloud coverage at all. You don't see any shadows really being cast whatsoever.
Let the woman go. You are under arrest.
You better back up, pal! He's gonna kill her! He's gonna kill her! I got this bitch! He's gonna kill her, man! This bitch! He's gonna kill her!
One of the interesting things about that clip is that it sort of gets beyond the notion of just figuring out people. It gets to the idea of figuring out intent, and I think this is a really interesting area going further. You know, right now we're at the stage where we're just being able to figure out which are the people and maybe what they're doing or what they're saying. But you know, to really start getting into the psychology and understanding what's motivating people, what they're thinking, what emotional state they're in. Are they scared? Are they angry? Are they happy? That's something, again, that people do extremely well. We're really well attuned to the kind of information that's conveyed by people's faces. And that kind of sensibility, being able to put that into a computer, it really starts to break down the lines between man and machine. And I think that'll be just an amazing direction as we go forward. I think that's, it'll be a hell of a lot of fun.
Bye.